Ever wondered what lurks behind the mysterious term negative energy? You might think it sounds like something out of a sci-fi movie, but it's actually a real concept in physics. Negative energy is like a hidden force that helps explain the nature of various fields, including the gravitational field and certain quantum field effects. Imagine if gravity could push you away instead of pulling you down. In the realm of quantum physics, negative energy can pop up in the strangest places. Picture a vacuum, you'd think it's completely empty, right? Well, not quite. Even in a vacuum, there are tiny fluctuations of energy that can momentarily create pairs of particles and antiparticles. These pairs can have negative energy, balancing out the positive energy in the universe. One of the most fascinating implications of negative energy is in the concept of wormholes, those hypothetical shortcuts through space-time. To keep a wormhole stable and open, theories suggest you'd need exotic matter with negative energy. This exotic matter would counteract the gravitational pull that tries to close the wormhole. But it's not just sci-fi fantasy. Talking about gravitational energy or gravitational potential energy. In classical mechanics, this potential energy is an intrinsic property of any two or more masses that exist in the universe. Here's where it gets interesting. Conservation of energy necessitates that this gravitational field energy is always negative. Why, you ask? It's because this energy is zero only when the objects are infinitely far apart. As two objects move apart, the gravitational force between them diminishes, approaching zero from the positive side of the real number line. Simultaneously, the gravitational potential approaches zero from the negative side. But what happens when these objects move closer together? As they draw nearer, gravity accelerates their motion, increasing their positive kinetic energy. To conserve the total sum of energy, the system treats this increase in kinetic energy as a corresponding increase in negative gravitational potential energy. In a universe dominated by positive energy, everything would eventually collapse into a big crunch. On the flip side, an open universe dominated by negative energy would either expand indefinitely or meet its end in a dramatic big rip. But there's another intriguing possibility, the zero-energy universe model. In this scenario, the total amount of energy in the universe is exactly zero. How? The positive energy in the form of matter is perfectly balanced by the negative energy in the form of gravity. Ever heard of the ergosphere of a rotating black hole? For a classically rotating black hole, the rotation creates an ergosphere outside the event horizon. Within this region, space-time itself begins to rotate in a phenomenon known as frame dragging. One of the most intriguing aspects of the ergosphere is that particles can escape from it. Within the ergosphere, a particle's energy may become negative due to the relativistic rotation of its killing vector. When a negative energy particle crosses the event horizon into the black hole, the law of conservation of energy necessitates that an equal amount of positive energy should escape. Enter the Penrose process, a theoretical mechanism that could explain some of the universe's most energetic phenomena. In this process, a body near the ergosphere divides into two. One half gains negative energy and falls into the black hole, while the other half gains an equal amount of positive energy and escapes. In the Casimir effect, two flat plates placed very close together restrict the wavelengths of quanta that can exist between them. This restriction limits the types, number and density of virtual particle pairs that can form in the intervening vacuum. As a result, a negative energy density is created between the plates. On the opposite sides of the plates, this restriction does not exist or is much less significant, allowing a greater number of virtual particles to form. The forces outside the plates are therefore greater than those between them, causing the plates to appear to pull on each other. This phenomenon has been measured and confirmed experimentally. More accurately, the vacuum energy caused by the virtual particle pairs is pushing the plates together. The vacuum energy between the plates is too small to counteract this effect, as fewer virtual particles can exist per unit volume between the plates than can exist outside them. In the realm of quantum optics, it is possible to arrange multiple beams of laser light in such a way that destructive quantum interference suppresses vacuum fluctuations. This arrangement creates what is known as a squeezed vacuum state, a state that intriguingly involves negative energy. Imagine light as a repetitive waveform, oscillating between peaks and troughs. In a squeezed vacuum state, the waveform is manipulated so that certain regions experience reduced fluctuations, while others experience increased fluctuations. This leads to alternating regions of positive and negative energy. According to the Dirac Sea theory, the vacuum of space is not empty, but filled with an infinite sea of negative energy states. This concept was born from the need to explain the existence of negative energy quantum states predicted by the Dirac equation, which describes the behavior of relativistic electrons. Imagine the vacuum as an ocean of particles with negative energy, so densely packed that every possible negative energy state is occupied. This sea of negative energy particles was theorized to be the true nature of the vacuum. When energy is added to this system, it can create a hole in the Dirac sea, which behaves like a particle with positive energy, an antiparticle. In 1931, the concept of negative energy was revisited, and with contributions from Hermann Weyl, it led to the groundbreaking theory of antimatter. This theory suggested that for every particle, there exists an antiparticle with the same mass but opposite charge. The following year, in 1932, Carl Anderson discovered the positron, the antiparticle of the electron, providing experimental confirmation of Dirac's theory. As we continue our journey, one of the most fascinating phenomena in theoretical physics is Hawking radiation. This concept, proposed by the legendary physicist Stephen Hawking in 1974, fundamentally changed our understanding of black holes. Hawking radiation arises from the mysterious realm of virtual particles. These particles can exist for an incredibly short period, flickering in and out of existence in the quantum vacuum. When a pair of such virtual particles appears next to a black hole's event horizon, a dramatic event can unfold. One of these particles may get drawn into the black hole while the other escapes into space. But how does this process work? When the particle is drawn into the black hole, its energy state changes. The particle's killing vector rotates, causing its energy to become negative. This change ensures that the pair of particles have no net energy, allowing them to become real particles. The particle with positive energy escapes as what we know as Hawking radiation, while the negative energy particle is absorbed by the black hole. The absorption of the negative energy particle effectively reduces the black hole's net energy. Over time, this process can lead to the black hole slowly evaporating. Talking about a wormhole, it directly connects two locations which may be separated arbitrarily far apart in both space and time, and in principle allows near instantaneous travel between them. Negative energy appears in the speculative theory of wormholes, where it is needed to keep the wormhole open. A tunnel that not only connects distant points in space but also bridges different moments in time. However, the practical existence of wormholes remains highly contentious. Physicists such as Roger Penrose regard such ideas as unrealistic, more fiction than speculation. Yet the idea of wormholes continues to inspire. The Alcubierre drive, named after the physicist Miguel Alcubierre, is a groundbreaking proposal based on a unique solution to the Einstein field equations of general relativity. In this theoretical model, a bubble of space-time is constructed using hypothetical negative energy. This bubble allows for the expansion of space behind it and the contraction of space in front of it, propelling the bubble and anything within it at speeds that could potentially exceed the speed of light. Remarkably, this concept does not violate the laws of general relativity. The contents of the bubble do not actually move through their local space-time. Instead, they are carried along within the bubble as it warps the fabric of space around them. This means that the ship inside the bubble would not experience the relativistic effects typically associated with near light speed travel. Could we one day harness the power of negative energy to explore the furthest reaches of space? Or is this another beautiful dream forever confined to the realm of science fiction? Speculative theoretical studies have suggested that particles with negative energies are consistent with relativistic quantum theory. Negative energy particles are often discussed in tandem with concepts like negative mass and time reversal. These particles could theoretically exhibit behaviors that seem to reverse the flow of time, a notion that stretches the boundaries of our comprehension. In the realm of relativistic quantum theory, these speculative particles are more than just mathematical curiosities. They interweave with the fabric of space and time, hinting at deeper, uncharted territories of the universe. Could these particles hold the key to unlocking new forms of energy, or even revolutionize our understanding of the cosmos? As we end our cosmic journey, the mysteries of negative energy remind us that the universe is vast, and its mysteries are endless.